And without further ado, Nikita, please take it away.
Yeah, thank you very much, Anya. Thanks, colleagues. I'm very happy to meet you here today. As was already mentioned, my name is Nikita. I'm based in Germany, in Munich. So as was said already, we have lots of snow. It's kind of different weather, but let me try to explain the background of the talk today. So today we will be talking about, and let me start with a slide. Let me know if you are able to see and to hear me well, right? Everything is fine?
Yeah, we can see and hear. And I should mention, folks can write questions in the chat and we can raise them. So feel free to add those questions.
Yeah, absolutely. That's very important. I will be happy to interact with you during the talk because at some point it may be quite complicated. And of course, there are lots of different ideas which I try to summarize, but there's still lots of information. And so today we will be talking about fraud detection with graph features and graph neural networks. That's the talk I presented already just one time at PyData Munich. And so that's the result of the last 4 or 5 years of work in the fraud detection domain. So I've worked with a fraud detection model since 2012. So I worked at SIS Institute, at SAP, at TigerGraph, and I worked with fraud detection in different domains, in banking, in telecom, as well in anti-money laundering domain, working with government authorities and with e-commerce fraud like ad-click fraud, etc. So I will be happy to give some broader overview on the direction of this area and suggest some technical or data-driven solutions, let's say. So let's start. So that's the good slide for 2021. We have, of course, 2023, maybe it's a little bit outdated, but I mean, we have even more fraud types in 2022, like authorized push payment fraud and the rise of synthetic identity fraud. Of course, since COVID, we have also fraud in the area of the COVID government support. So there are lots of different types of fraud which grow every year. We have fraud in social networks like fake account detection. Netflix is suffering from misinformation propagation, which we have on many social networks due to echo chambers and not enough diversity in the recommender systems. We have lots of fraud in the domain of finance, in insurance, in credit scoring, which is called like first payment default. Of course, we have money laundering and we have transactional fraud. Pretty large amount of fraud is happening in Bitcoin, and in darknet, for example. This particular year, the large amount of fraud was connected with the war and when the sanctions. For example, some people from Russia, they wanted to move the money to Asia, and then they buy some synthetic identity in the darknet to open the account in Indonesia, and then move the money to European Union to pay for the yacht. I mean, there are lots of different examples which were uncovered by police. So of course, it's important to detect them early, especially if it's about, large volumes of data. Of course, some big cases, for some big cases, we require deeper investigations, but for large volumes of data, which is the case for the e-commerce fraud or transactional fraud, etc., we need to have some automation. And this automation, it's still in the development. So still lots of the banks employ the rule-based approaches and even not the simplest machine learning models. So it's important, depending on where you are on your journey, it's important to understand what next steps you may do to make this process iterative, to start with kind of low-hanging fruits, because yeah, I mean, especially every data-driven and fraud detection practice in bank, in telecom, in any other company may have lots of problems growing, because you need to show the impact you provide, and of course some people may have a resistance to what you're doing, because you kind of trying to find the areas where they are not working perfectly and where they have some gaps. So you have to collaborate, of course, a lot. And yeah, of course, you have to build solutions which impact some KPIs and key performance indicators, and which bring some money to the business in the end. And I will show you as well with the code example how we could calculate the money impact from the simple machine learning model with some graph features. But yeah, let's go further and try to answer some very important question for this talk: why use graph for fraud detection? So I mean, that's probably the most popular question on interviews if you talk about fraud for machine learning and data science for fraud detection, about the class imbalance and how you should fight the class imbalance. Very good question, and I think it's still very relevant for industry and the practice. So class imbalance, as well as label scarcity and fidelity, is still, I have to say, not really solved problem in the area of fraud detection, especially because there is kind of not survivorship bias, but still some fraud may be undetected. So if you have the negative label for some transaction, it does not actually mean it's legitimate, because there may be some type of fraud you just didn't know it exists. And so that's one thing. Another thing that of course, yeah, fraud types and practices, they change over time, and today even faster and more frequently. So with the rise of different platforms, payment methods, and lots of startups to run your payments across the world, you may have even more fraud. And yeah, especially it's difficult for also international money laundering activities, but yeah, that may be completely different topic. So yeah, I mean, the second topic is the fraud camouflage. It's like also the important factor which makes the whole task of fighting bad guys difficult. You have context and feature inconsistency. So fraudsters may try to hide the activity. They may connect to regular entities, for example, for DDoS attacks or some botnet attacks in internet. No one use their personal computers or notebooks like it was maybe 15 years ago, right? Everyone used a dedicated server, which is infected with the malware. It's infected from probably another server. So you have really lots of steps which are used to hide the illegal activity and to make it complicated for you to understand, is this entity you are looking at right now actually legitimate or not? Because yeah, it may be compromised in some way, to some extent. Yeah, and it makes especially data-driven approaches very difficult, because you may have the features of the entity which show that's actually legitimate, but the behavior is more similar to fraudulent. And at the same time, there is lots of activities associated with fraudsters changing their identity. I mean, and here I mean identifying attributes. There is this popular example in the area of misinformation propagation that one particular account in a social network was able to get from, I don't know, 3,000 to 70,000 followers in 3 months. And this account was changing identity, and I think it was actually connected with California, because when there were forest fires, the account was changed to the identity of firefighter, and he was posting the photos with the fire and saying how people suffer fighting the fire and etc. And next time when it was some the event with a ship, that was changed to the ship. The account was changed to the female ship crew member, and she was posting also the photos from the about the events at the ship, what happened. I don't know, there was some emergency or something like that. So yeah, it's just these are just examples that again, fraudsters may change their identifying attributes, right? And that's the same like with social security numbers and etc. So it makes the data-driven approach, of course, difficult, because you cannot actually associate the proper weight, proper scoring factor with the attribute, which is not something you could trust fully. So yeah, of course, graphs are useful to run investigation and exploration, and they're used for the last, I think, 30-40 years since first computers were created. I mean, if you've seen movie, one of my favorite movies, The Wire, about the police investigation, they always have this whiteboard where they have the photos or the bad guys, and then they connect them with the edges and try to understand how they could plan the operation in some way that they will have the evidence. I mean, that's still very much used. You can follow such colleagues like Chris Westphal, for example, who is using graph analytics with such technology like visual links. So visual links technology is very famous because it was used in Department of Justice, in FBI, and in many other. So that was just kind of graph exploration toolkit, which allows you to click on the node and see what are the neighbors of it, but we will go to that later. So anomaly detection is also very, very important in fraud detection, or kind of unsupervised way to detect anomalies, just because in some cases your labeling, maybe, as I've said, you have labeled scarcity and fidelity problems. It may be very much unreliable. And here I may give just an example from talking with the member of government authority in the area of anti-money laundering. So we were talking about applying machine learning for anti-money laundering task, and he explained that if you have the suspicious activity report filed about, you know, some person or operation or the company, you cannot actually consider it the positive label for fraud, because, or positive label for money laundering, because to be able to state that, you need to wait while the court will actually look at that and make a decision that they, again, some people may not know that they are involved in money laundering activities. So there are also the type of fraud which is on the rise in 2022, which is called money mule fraud. And yeah, sometimes people even didn't know they were involved into some activities. That's about the cases when, you know, you meet some guy somewhere, you start to play, I don't know, golf with him, and at some point he asks you to use your car to drive some package somewhere, and eventually, because yeah, his wife is busy and this is the package with the meal for his kid, so you need to drive it from his work to his home, and and then in the middle you are stopped by the police and then covered lots of money, and yeah, etc. So there are lots of such stories. If there are lots of books which are written by the former FBI agent with such particular examples. So yeah, and money mule fraud, yeah, was especially very important for 2022, because lots of people were looking for synthetic identities, and yeah, some people were providing their identities just or their credit card details without proper understanding. Of course, yeah, we may say we need to raise the financial education level here, but that's also another topic. So graph embeddings. So graph embeddings is already kind of step forward. So this is the way to use some simple neural networks to run representation learning on graphs and get some kind of adaptive features which encode the structural information, because in some cases we may have the fraud patterns encoded as the part of the transaction network. That could be fraud rings, that could be this structuring, placement, layering, and integration structuring activities. That could be the loops when the money goes from one destination back. That could be some triangles when there, I mean, too many loops, because they would like to structure money and bring them again back to the original destination. So of course, different structural patterns are also useful, and especially combined with natural language processing, like if you are able to spot particular names or particular destination like Cayman Islands, etc., or Albania, if we talk about Europe. So that's also may be a good explanatory factor for the risk. And then, of course, we have explainability and fairness. Explainability is extremely important in regulated industries, right? Like in credit scoring and then fraud detection as well. So context structure, which is given by graph, could be used for interpretation. And we will show today in the code example how it could be done. Basically, you could extract the subgraph from your graph and show the same like with usual explanation approaches, when you show, okay, how this particular feature or this particular value of the feature influence the final prediction. In the same way, you could show how the subgraph, which is associated with this particular node, with the classification decision, how the neighbors are influencing the decision about classifying this node as fraudulent or not. And of course, you could also use a graph for debiasing, for fairness, because let's say you have the interference between the samples of your data set. For example, you have the members of some social network and they're connected to each other. And if you'd like to debias the data set, and you'd like to balance it, I don't know, by the age or by sex, for example, you need to understand interference, because some people there is such effects like homophily in social networks. So we could be connected to similar individuals as we are, right? And if we will not take into account that fact, we may just fail with balancing the whole data set and the whole set of experiments if we talk about A/B testing. Yeah, but that's again much more advanced topic if we talk about fraud detection. Okay, so let me present you some simple data model which will be used in our use case today. So This was the data model from the real bank. So yeah, we have the following entities like account, transaction, and usually if you look at most of the use cases in transactional fraud, because today we'll talk about transactional fraud, could be represented with a bipartite graph. So bipartite graph, we have account and transaction. So for one account, we have many transactions, and we have some features of account, features of transactions. Of course, we have labels for accounts. Yeah, so, and then of course, this graph is temporal. So we have more transactions and more users coming with time. And yeah, we also have some features. So yeah, that's the 90% of the fraud cases could be casted to such kind of representation, to a bipartite graph. To some extent, it's similar to recommender system where we have the user item, right? Bipartite graph. Yeah, so again, we have an account and transaction. For the transaction, we have some attributes like what is the state of transaction, if it's failed, completed, or reversed, or there is a chargeback. We have the type of transaction, if it's a fee or if it's a money transfer, if it's ATM withdrawal, we have the currency, if it's United States dollars, if it's euros or some other transaction, some other currencies. We have an hour of transaction, for example, it could be afternoon or at night. And based on that, we could create some set of features. So we try to represent with these features something really, we try to make the feature set representative. That's what I wanted to say, because of course in production you have much more features, but we try to make this particular feature set diverse for you to understand what are different types of them. So out of this graph data model, you could create the feature set, which could have such features like first digit of transaction and last digit of transaction. So, let me explain you what the actually the fraud use case is here. So we have the transactional fraud, which is called top-up fraud. Top-up fraud is basically the type of fraud when you have your credit card and the fraudsters are using stolen authorization code, SMS code to authorize the top up to their credit card from your credit card. So you just look at your iPhone and you see you just made a top up to someone's credit card, but you have never approved it because the authorization, the SMS code was stolen. So actually SMS is very insecure way of communication that was communicated to many banks across the world, and many of them are already using more secure ways of communication. But some of them are still using SMS. So so stop using SMS if you're still doing that for authorization codes, and ask your bank if they have alternative options for in Germany, for example, it's called Fototan, so it goes directly to the application. But in US, probably you may have something different. So
that's good advice. If I can interrupt, we have a question. Zayan asks, will type be a super node because all transactions in ATM will be linked?
I mean, of course, the nodes will have different cardinality, but I mean, I don't think we have. So of course, in the real data model, we will have not only the type, but also merchant category code. And then for every ATM withdrawal, we will have the merchant category code, right? Merchant category code. For every purchase, we will have the merchant category code. And we may not need all ATM withdrawals. Again, we may use some pre-aggregated data, but you are right. That in reality, we will have lots of ATM withdrawals as the transactions, and we sometimes we need to find a better way to deal with them than just store them as a raw data, right? We need to pre-aggregate them in some way, for example. on a daily or on a weekly basis. And there is some story about that. So at some point we worked with the bank and we did exactly like that. We pre-aggregated all the ATM withdrawals per account, but it wasn't exactly per account because we were building the golden record of the customer. So there were many accounts like the current account, deposit account, etc., credit card, internet banking account, and we were linking them based on the person. So we aggregated ATM withdrawals, and we found that one person has, I think, 60 ATM withdrawals per week or so. So he was doing like 12 ATM withdrawals per day. So that was really high velocity. Wow. Yeah, I mean, we sent this case to security department, and they started an investigation. So the original thing which was found, because that were linked to a similar persons, not with the absolutely similar name, but with a similar attribute. So the actual case that was found, that there were dead people who the customers of the bank who were dead, and then employees of the bank, they see that there are accounts and they know already that people are dead and nobody comes for the money because they don't have children, they don't have anybody. So they are trying to open accounts within the bank and transfer the money from these accounts to their accounts, and then for their friends, for their relatives, and then they were just trying to get it out of the bank in a cash. So yeah, that was, I mean, of course, it was quickly found, but it was just one of the examples for this question. So yeah, I mean, of course, for ATM withdrawals, we have pretty high velocity, and you are right. If we have a super node, we may need some specific types of data distribution to be able to work with the graph in a scalable manner. Yeah.
Awesome. Thanks. It sounds like that was a good answer for Zian.
Yeah, I mean, I like this interaction because probably I have a story almost for everything which we discuss here, because as I've said, it's not the talk about some proof of concept. It's the aggregated talk about 4 or 5 years of experience, which at some point I decided to express in such kind of public notebooks and examples. So yeah, let me go to the features again. So we have first digit and last digit of transaction. If you heard about Benford law, you may know that first digit and last digit of first digit of transaction is distributed exponentially. So if you take the transaction history, then the most popular digit will be 0. The most popular first digit will be 1. The second popular first digit will be 2. The third popular digit will be 3. So it may sound illusional, I mean, so it may sound, but yeah, actually just check out Benford law. It's used in lots of fraud detection rules and models. So it basically allows you to support some repetitive amounts, right? Like 5,500, 999, and it's usually helpful because fraudsters sometimes are bounded with some, you know, they need to come up with some kind of, when they do structuring or fraud, they need to come up with some kind of random amounts, not to be spotted, but they still have some reporting threshold, for example, $10,000, and they have to be a little bit lower than reporting threshold, but not very much lower, because if they will be very much lower, they will need lots of money mules. So the transactional cost for this money mules for carriage of this fraud will be too high. So there is always the bias towards a particular amount, and these things like first digit or last digit could be useful to spot it. Then we have usual aggregate features. If you work with classical machine learning models, it will be fine for you. So like counters and averages and number of, for example, number of unique states per transactions, number of average amount of top-ups or number of top-ups. Of course, we have country of the transaction.
And Nikita, are these part of the feature set, or?
Yeah, it's part of the feature set. Yeah, exactly. Yeah. So it's like the tabular data. Yeah. So that's what was calculated. I will show the notebook how it was calculated. So yeah.
Okay, so Jaden, your question should be answered when Nikita shares the notebook as far as which part is the target set, which part is the feature set. Great, thanks.
Yeah. The target set is just about the top-up fraud. It's the binary variable 0, 1, but yeah, that's just the explanatory variable. So we have also very important variable about velocity of the transaction. For example, it could be average time between transactions. We have the standard deviation of transaction amount. We have the hour of transaction to spot some transactions which are done, I don't know, at night during holidays or some, it could be done with the day of weekend, etc. And we have a couple of graph features already here. So we have 4 graph features. So that's Louvain, and yeah, let me introduce. We will use 2 graph algorithms like Louvain community detection and PageRank. I hope everyone heard about the PageRank. That's the famous algorithm which was introduced by Google founders Sergey Brin and Larry Page, which measures the importance of the node in the whole network, kind of. So like in the same way like influencers are important for the whole network, the nodes in the transactional network, which have lots of incoming and outgoing connection, will have a higher page rank, and this way we could correlate it with some fraud patterns. And Louvain community detection is a smart way to do clustering in a very scalable manner. So it's a way to do clustering with n log n scalability. So you could actually do it for the 100. You could easily do it with 100 million size data sets, and with some decent hardware you could do it also for several billions data set. At the same, if you know, most of the clustering algorithms are quadratic or cubic complexity, like agglomerative clustering or hierarchical clustering, and even k-means. It's widely used in industry, but we still read lots of papers like there is no good way to define the number of clusters, and we know that the spherical assumption is not that good. So Louvain community detection is a very good and non-parametric method for clustering. Even if you don't have like natural graph in your transactional network, you may still use the bipartite graph like user account or user item. You could calculate the graph as KNN or nearest neighbor graph or approximate nearest neighbor graph based on user similarity. For example, when you don't have transaction, and on that graph you could also use Louvain community detection to basically select and have the communities. Yeah. These are some real examples of the visualization. So, of course, you may use graph for exploration and investigation. This is example of the larger portion of several thousand of nodes. Of course, not the whole graph. In this example, we are talking about the graph of several millions transactions. Several thousands may look like that, and that's already sometimes difficult to look at. You need some possibilities to filter, to add some context, to add some colors. And of course, you could start not top down, but you could start bottom up as well. For example, you may see that there we have a particular account, there we have one more account. This account has is doing transaction during early afternoon hours in the currencies like euro and I don't know, RON, and for example, it has some transactions which are reverted, and this account doing transaction during late afternoon hours using Great Britain pounds currency, card payments. Some of the transactions are declined, but they also have something in common. For example, both are doing transfers, both have some transactions completed, both are doing some top-ups, and both are doing transactions which involve commission fee. And on the edge, we store also the number of such transactions, and it's about the question about the super node. So yeah, of course, we pre-aggregate that. So we store on the edge the average amount of, for example, fee transaction or average amount of transfer, standard deviation of the transfer, amount of such number of such transfers. So the usual aggregations like count, average, maximum, etc. So yeah, I've mentioned already feature engineering and feature engineering, and let's switch actually to the real example. This is
we should probably talk for 10 more minutes, and we'll save 10 minutes for questions.
Yeah, okay. So yeah, this is an example. Let me show that. So yeah, this is an example of the notebook which will be shared after the presentation. So yeah, we have the feature engineering, where we define all these features which have shown, like if it's a fraudulent transaction or not, if it's a first digit of transaction, last digit of transaction, different aggregations, and then we encode country with the label encoder, and we calculate average time between transactions. And then we calculate graph features with the Louvain clustering, and this is a visualization of the graph clustering based on Louvain. Then we calculate graph features with label propagation, and then we could actually look at the percentage of fraud by the first digit. You see some first digit like 5. They have actually much larger amount of fraud. Let me make it bigger. Yeah. For example, the first digit like 5 has much larger amount of fraud, and the first digit like 2 has also large amounts of fraud comparing to non-fraud transactions. Then we could also look at feature importance, right? And we see that the Louvain community is the first most important feature, and the label propagation community is the 5th most important feature, despite the fact we have really powerful features here, like, you know, country and number of top-ups and etc. Then we also have the calculation of the money impact by the model. We have the saved money from the true positive prediction, and we have the cost of the false positive prediction. And then we could calculate not only the usual metrics like F1 score and accuracy, precision, and recall, but we could actually calculate the revenue from the correct prediction and the cost from the incorrect prediction, because we know what are the costs of false positive, what are the costs to unlock incorrectly locked account or check the locked transaction, what are the approximation of this cost, and we know what is the average amount of money which could be recovered given this case of transactional fraud. And then we could calculate the revenue and cost for every threshold at which we'd like to block the transactions, and then we could look at the chart, and we could actually, with a simple Python function or we're using the chart, we could make a decision which threshold to use to block transaction, to check transaction, because we try to find kind of point of the optimum after which we have more false positives than a true positives, and then we have the profit from our model going down. So it's the financially grounded way to select the better model and etc. I mean, of course, it's using some approximation, but it's important to remember that costs of your false positives and true positives may be different according to the industry where you try to apply machine learning. Yeah, so yeah, that was the code example with the graph features, but I would like to remind that in production that may be much more complicated because you need to calculate graph features only on a trained part of your data set to avoid leakage. You need to also use only trained labels to calculate graph features like k-hop distances from the current sample to the nearest fraudulent sample. You need to use time-based split because random cross-validation was never useful in production. And yeah, and you need to also be able to calculate features in a temporal way, because once you have a new transaction, you will need to calculate the page rank and Louvain community for the new transaction. You will not be able to run this algorithm, you know, from scratch for every new transaction coming from the Kafka stream. So the idea is that you need to use actually inductive or temporal algorithms like the temporal page rank or dynamic community detection. So, I mean, you could read more about that in the presentation. I will share that after the end of the talk or in the couple of my posts that I have on my LinkedIn page. The most important is this, one of the most interesting is this slide, which shows the gap between precision recall curve with and without graph features. So of course we may look at financial impact, but data scientists are always interested in the actual, you know, accuracy numbers or precision recall numbers. So we don't show point-wise precision recall, we show area under precision recall curve, which is the best metric for imbalance data sets, and we show that this is the area under precision recall curve without graph features, and this is the area under precision recall curve with graph features. So we see the gap between them, which shows the aggregated impact of graph features like Louvain community or PageRank. And yeah, then there was a slide about how to run explainability on top of that in a scalable way, because yeah, I hope most of you know how to run it with shapely values, but we know that shapely values is using sampling to calculate feature importances. So sometimes you cannot apply it to a data set 100 millions or billions of records. You will never be able to apply shapely values without very big downsampling, and it's not appropriate because, of course, if you have large high cardinality attributes, then the sampling will be unreliable. So yeah, but there will be a notebook about this explainable approach with the XGBFIR library, which allows us to use feature interactions for the explainability. But the last part of the talk was actually about using graph neural network because it's more adaptive way where you don't need to generate features. You may actually use neural network to extract the structural patterns from your data. And yeah, this is an example of area under precision recall curve for the graph neural network. So we, for example, yeah, here area under precision recall curve was around, yeah, this was around 28%. This was, for example, 35%. And we see that for graph neural network, it's reaching 40 or even 50%. But the most important thing to share that we were running hyperparameter tuning with Aptuna for around 2 weeks, right? To actually find the optimal hyperparameter to find the better performance, because yeah, of course, it's difficult to fit neural networks on unbalanced data and especially on a graph data. These are some examples of explanatory subgraphs from the fraud data set. Unfortunately, I cannot use some labels and attributes on the visualizations because these are part of the these are part of the data set, which I cannot disclose. I will be able to share just the code. But yeah, these are some examples when we see how fraudulent nodes, these rosy nodes, are connected to legitimate nodes. This is particular data set that we used for phishing fraud detection. And yeah, I think that's almost everything. So let me also show you quickly the notebooks which will be shared after the end of the talk. So 1 second. There will be explainable fraud detection with graph features data set, which shows how to convert.
Fabulous.
Yeah, how to convert the model into explainable rules, because some banks and corporations, they still like to have the explainability and simple rules to integrate it into production. And there will be also data set with the graph neural networks trained and with the explainability and how to run graph neural network explainer and etc. So yeah, I think the talk was a little bit unbalanced, so we had lots of information in the end, but I hope I was able to give lots of interesting examples around fraud use cases, so to inspire you to work in this domain and build more adaptive and scalable models. And I will be happy to answer your questions. Yeah, thank you very much for your question.
Thank you so much, Nikita. We do have several questions, so thank you. On behalf of us at Big Analytics, we're so happy that you're here. Nikita's slides and notebook will be shared, as well as the video recording, on our Meetup page, as well as our YouTube channel.
Absolutely, yeah.
A couple questions. So in addition to the notebooks, are there any other tools that you use as like graph tools?
Yeah,
or is that all that included in the notebook?
Yeah, we for the storage of the data, because of course there were quite big data, around 100 million transactions. We used the graph database TigerGraph. It was actually at the time I worked at TigerGraph, before S&P Global, but it's very similar to, so I mean, we were using just PyTorch sampling, so you could sample from TigerGraph database in the same way like you could sample from PyTorch dataset, right? From the CSV or any other type which you actually map or connect to a PyTorch geometric dataset. So yeah, that's the only, I think, still proprietary technology I've used in the graph neural network, but all other technologies are open source. And for really large sets of data, especially for such, investigation and exploration, we still may need some things like the databases. But I think that's quite natural for everyone.
Yeah, thanks. Another question, Tiago Oliveira asks, is the latency for response prediction somehow sensitive for the consumer applications of this GNN model? Absolutely. And if so, is there any tactic to speed this up?
Absolutely, because the model is trained on subgraphs. You need, during the inference, you need also to sample subgraphs, right, when you run the inference. And the thing is, accuracy is very dependent on the size of such subgraph. So if you do prediction, you need to sample the subgraph. It will be a small subgraph, then the accuracy will be low. If it will be a large subgraph, then the inference time will be slow. So that's very difficult problem for JNNs, because, and in the end we try to do the following, like sample many different small subgraphs and then use kind of an ensemble of prediction and make the inference in parallel using some again GPU devices, etc., and then aggregate the predicted result. So this is some way to find the balance between latency and accuracy, but this is still very much open question. That's
sounds like an open challenge. Pankaj asks, Can you say what was the stack used for these analytics, especially with GNN?
PyTorch geometric. PyTorch geometric.
Great.
Of course, you could use deep graph library from NVIDIA and I think AWS. You have PyTorch geometric from Kumo AI. So yeah, they are very similar in terms of functionality. Yeah, and there are lots of other frameworks like TensorFlow, JNN, for example, if you like TensorFlow, and dive-in graphs and AutoGL, like there are also AutoML frameworks for graph learning. Yeah, there are plenty of them. I try to post sometimes also at LinkedIn about different frameworks. Yeah,
for sure. And we'll ask one final question. How do you decide the feature set?
Yeah, I mean, that's I think that part is the most creative part of the whole data science process. So you need to combine some domain knowledge, some creativity, some luck as well, some understanding of how machine learning algorithms look at the data. Because I mean, we know that, I don't know, some variable encodings may work with some algorithms, like, you know, label encoding or target encoding may work with gradient boosting, and one-hot encoding works better, for example, generally with logistic regression. But it doesn't mean that you cannot make gradient boosting work with one-hot encoding or vice versa. Yeah, some understanding of how algorithms look at the data, and also understanding how business could make some inference from the data, especially given the fact that some features needs to be computed in online fashion, as I've said, not just the graph features, but also count features. If you heard about such structures like count means cage, or hyperlog log, or min hash, I mean, so I mean, you need to calculate the features in an approximate way, because yeah, you have the streaming data, and at the same time you have the business analyst, fraud business analyst, who is saying, I cannot accept the approximate value of the feature, because if we run the investigation, we need to have the precise value, which we will submit as a part of suspicious activity report for a government authority. And then you need lots of hardware as well. So you need to explain this everything for the budget owner. So yeah, it's a very creative part of the process, creating the features. But I like to say that despite the fact there are still there are already graph neural networks and etc., it's not that oversaturated field yet. Like like natural language processing or computer vision. Despite the fact you use graph neural networks, you still have to generate graph features and all other features which you feed into graph neural network. It's not the same like with natural language processing, where you just apply, you know, tokenization, positional encoding, and then you have a transformers like ChatGPT learning everything via multi-head self-attention. It's still very much a manual process where you could still apply your curiosity and creativity. And yeah, that's why I like that. But yeah, maybe it will be much more automated in the future. Looking forward to that, when we were able to run neural networks without such deeper understanding of yeah, what could be done, how features could be generated, and what is completely nonsense in terms of the domain knowledge. But yeah, thank you very much. They were great questions.
Yeah, there's actually a lot of more great questions. So if you want to stay on afterward, that would be great. For a few more questions. But thanks everybody. Thanks for joining. This has been a great talk. Thanks Nikita for sharing. There's clearly a lot of room in the space, a lot of room to grow and be curious. So if anybody's interested in getting into fraud detection, it's a good career path. So thank you, Nikita. Thank you to our partners, AI Camp. And I will stop the recording. But if anybody wants to stay on and ask questions, Nikita, if it's okay, if you have a few more minutes, I can allow people